Yeah, it was nice to come out.
That's one thing about Mario.
Right. Do you know, I was about to say, is it March? No, it's February. Good evening and welcome to February. It's been a challenging few weeks. January felt like it went on for a long time, didn't it? So, you know, I can forgive you for that. So, look, welcome. Thanks for coming. It's nice to see the weather's a little bit milder. It's great to see so many faces here, as always. And, Tony, are you recording this?
Unfortunately, yes.
Right, I've forgotten about that. And I feel absolutely... Right, anyway. Right, so I'll get straight on with the introduction. Thanks for coming along tonight. I feel quite self-conscious all of a sudden when I'm going to start doing this with my glasses now as well. Right, Dr. Joseph Barnard grew up in South Africa. He came to the UK in 1972 when he got a B.Sc degree in applied physics at Essex University and an M.Sc degree in solid-state physics from the University of Birmingham. He then went to Cornell University in the States where he completed a Ph.D. in Electrophysics, where he worked with, is it pronounced Hideo Ono?
Hideo Ono.
Right, okay. To develop the first...
Gallium, indium arsenide, transistor.
Right, exactly what So, you know, it's because you've got the camera. It's because the camera's there, isn't it? I normally don't do too bad a job. Right, come on.
It takes
Right.
2 volts to switch around.
Right, on returning to the UK, he worked at GEC Hirst Research Labs in Wembley, after which he worked as a consultant in the development of optoelectronics devices in Hewlett Packard, in Ipswich, at Bookham Technology in Abingdon, and at Marconi optical devices at Caswell. Since 2010, he took up a childhood interest in UAVs, often called drones, and is the MD of Barnard Microsystems Limited, working primarily on the development of remotely piloted aircraft and on related systems and sensors. Since originally giving this lecture some time ago in Farnborough, events in Ukraine have confirmed the effectiveness of the use of multiple UAVs. I will get off the stage.
Thank you very much. You did a good job. You did a good job. So, thank you everyone for coming in the first instance. The way we're going to run the presentation is you're invited to interrupt at any stage and ask questions, because sometimes there are acronyms, for example, and I'd hate us to go on and you're wondering all the time, what is that acronym or this acronym? So do feel free. We'll also take questions. I'll take questions at the end as well, so if you wish to ask questions, or if you wish to not ask them publicly, then obviously I'm happy to talk with you individually. We're working with the MOD, DSTL in particular, so I won't be essentially delving into any classified information, so I'll back off from that for obvious reasons. We'll start then. Get this little thing to go forward. So, right. I think I have...
Yeah.
It did work earlier. It did work earlier.
Two of you, let's make sure you haven't got one. We have two, neither of them will work.
Yeah, but there's not all
I'm going to cover the unmanned aircraft, which are sometimes called drones. Sorry?
I told you we shouldn't use museum laptops.
You can actually do that. You can actually do that one. The big one. The big one. Okay, no, that's fine. What we're going to look at is the difference between, because one often hears the use of the word swarms. Now we've got this thing on auto.
PowerPoint has nothing to do with me.
UAVs. Now, some of the discussion has been taken, if you like, emphasised.
Young kids to come and sort this out.
Yeah, it has been really emphasised, but if you're looking at what's been going on in Ukraine, we see the effectiveness of the use of multiple UAVs in a military context. I'm talking about also the civilian context, so it's not only in the military context, but certainly very graphically you can see clearly that the use of multiple UAVs in an application, what often they say it's like guerrilla warfare, it's a weapon of the weak, but it's not a weak weapon. And these days, when one is in this business of sending expensive missiles, for example, to do the job, or aircraft for that matter, what we're finding is that actually money matters. So it's, in a sense, nothing new. but the financial aspect of the solution is massively important. Looking at what interest is there in UAVs, in case it goes, sometimes one can get in a silo where one can think that, for example, military applications are completely dominating the drone environment. They are not. Because you find, for example, mapping and surveying, massively important, using DJI Phantom type multi-rotor UAVs, and a whole host of other military security, monitoring, for example, the shipping in the channel, and civilian applications are there. So we're talking about essentially the use of multiple UAVs, either in a formation, and for example, when we were just talking just now about, if you look at a display, you have a whole lot of multi-rotors making up a display in the sky, which is very impressive. That's a formation. Or when would you use a swarm? So they're all like a swarm of birds, all flocking everywhere. So essentially allowing for redundancy, but not necessarily the most efficient solution, but they are a redundant solution. So if one drops out, one other one will take their place. So I just want to emphasize that this is essentially a combination of applications in military, in security, and in civilian applications. Starting first, and I'll go through some examples. Starting first with defense, we're working in defense with MOD. And one of the things you might ask if you're given the task to try and stop.
I have no idea what you've got set up on your laptop. Go back on that one there.
Yeah, go back on that one. So
What I suggest we might want to try is clicking on that there.
click on the big one down here.
Yeah.
Okay, let's see how that
Do on
goes.
the advanced arrows. Hopefully it's not going to go on again.
No problem. Right. So,
I'm going into the settings.
I tell you what, if I say next, then you be the good lad.
Oh, I'm going to be
You do the next.
Yeah.
Thank you.
I might have to keep going back then.
Right. If you're given the job, let's just say that we have 350,000 folk that we're not happy with, invading some place, and you need to stop them. And you need to stop them cost effectively. It might give pause for thought that actually trying to go out and kill 350,000 people is not a great idea, because another 350,000 could well appear. So the strategy that is often considered more effective is to actually deal with the infrastructure, i.e. the food. Because when the soldiers don't get the food, they're not very happy, and they're not, essentially the hostilities could well fade away. So essentially you target the logistics. You target the supply of the oil, so then the vehicles don't run. And that will just take care of the 350,000 people that are giving you a hard time. So often when folks think that it's some sort of like strategy game where you've got to try and destroy lots of people, I think that's misplaced thinking. And it really is considered to be one of money. Can you afford what it is you're trying to do? So it better be inexpensive. So this idea that you're going to have shed loads and shed loads of expensive missiles to do the job, as the Houthis are showing, for example, in the Horn of Africa, is got problems with that strategy. So basically, what they're saying in the military application is they might say, well, you've got to target, and I'm not an expert on oil fields, but let's just say somebody says, this is the thing you need to target. So we need to have one-way mission UAVs that will go and precisely target somewhere where there's no GPS guidance, because the GPS will be jammed at locations like this. So you need to have some navigation scheme, which is actually not easy. To go within, for example, 2 meters is often what's quoted, circle of error probability, over 200 kilometers. So if you think you're going to get an inertial measurement unit with magnetometers, accelerometers, gyros, and if you think the drift will be such that you can have 2-meter accuracy after 200 kilometers, then MOD would like to hear from you. So, next one. The other thing you need to do is essentially identify military vehicles, which may be well confused. So look at the imaginative camouflage that you see on this diesel supply. So here, you can see what's being supplied. It's clearly not a civilian vehicle. Yet, if you sort of saw that on the road, you can see the complexity of the job, that just because you've taken a photograph, and just because it looks like a civilian thing doesn't mean to say it is. So you need to have a means, sensors on the UAV, because if you have a lot of UAVs and you're looking at a lot of these things, you're not going to have a whole lot of people, and you're very unlikely to have the bandwidth of the communications to send all that video imagery back. So the UAV must have sufficient brains on board to pre-filter things and decide that actually this is not what it might appear at first sight. So it's a very challenging sensor requirement for the electronics that goes on a UAV. That has a weight implication and consequently a size implication to the UAV. But on top of that, you've got a budget. And that's something sometimes people in this business don't take into account, is that it better not cost more than £75,000, for example. It's often, anything that's costing more than that, it's like, you and I are on the wrong side of the store.
Next.
Please. And then if we look at a civilian mapping application, where the idea is, if you had a single UAV and you needed to map that area shown there.
That one there.
So you've got to map that. Now you can essentially say, right, get a single UAV and do that. The problem here is, again, it often comes down to money. And often in technical presentations, people don't talk about money. But money is massively important in this area. You need to factor that in. And the problem here is that every UAV, you usually have 3 people. You'll have the pilot, who's legally responsible for the plane. If anything bad happens, the pilot goes to jail or something like that. You have the co-pilot who will take over if the pilot is tired or unable or done a long stretch or feeling unwell. And then you'll have the payload operator. So now if you're looking at the economies of scale and you think, well, hang on a minute, if we had 2 planes, but the one pilot is managing both planes, suddenly we're saving money. Up to the next one, please. Oh, excellent. Whoops. So that would be then a fusion of stitching all the imagery together that has been taken to give you a very decent quality map of the underlying terrain, which we did on the south of England. So you can then run over an area. But the thing is then, if we're looking at cost, so let's just say you've got a small business and you're essentially running a mapping service. Here's when you start thinking, well, maybe if you had 2 planes, and that's where you're moving into a swarm or a formation. And actually for efficiency, you'd actually go for a formation, because it's essentially a fixed grid that you're flying on, so you can always put exactly the planes where you want, and get 3 or 4 planes. So for example, you get it done in half a day, job done. Then you move on to your next job, and you've only got 3 people who are doing a massive mapping operation. Obviously, you've got the initial capital cost of the UAVs, which comes into the whole business of, is this a viable business?
Next one.
Right. Okay, I think, all right, let's go hop to the next one. In a magnetometer survey, so this is what often the oil and gas people will be doing, is they'll measure the Earth's magnetic field by getting the plane to go up and down, as you see, left to right. Here's where you have the ground control station. So you'll have the 3 people and a truck, and they'll be managing the plane, doing a raster scan of this particular area. Okay, just don't try to be too quickly. And from which you can then form, if you're measuring the Earth's magnetic field, you can then, if you're somebody in the oil and gas business, you can work out whether there is oil there or not, or some other mineral that you're looking for example, iron ore in particular. You can work out where are the deposits, where should you start drilling, or mining rather, and clearly you can see that that looks like a good area to start. So you can do surveying, geophysical surveys, using the planes. And you can see all of these, it just comes to the same thing. Actually, if you used more than one UAV, you would make more money. Thanks. And I'm going to go through several examples where you can see here is in oil pipeline, and what you have then is a right of way, and you want to monitor that. And the reason is that you'll find enterprising folk will tap into the oil pipelines, siphon off oil, and in fact, sometimes it's so prevalent in Nigeria, for example, they have one where they have the oil wells, a location, and they have a refinery, and actually no oil reaches the refinery because they're all tapped off en route. And the problem is, the folks are not only, got a lot of initiative, they're very fast. So as soon as you close one down, another one springs up somewhere else. And so they've not been able, over several years, been able to open the refinery because they don't get any oil through. So then you're thinking, you know what? send the planes up, and then you have to send several planes up because the folks are so quick that time is of the essence. Another application is if you're using a down-looking laser LiDAR, so you're basically looking at reflections from the underlying terrain. So the beauty here is that if you shine a LiDAR down on vegetation, what you can look at is the first reflection. The first reflection will come from the top of the trees. But if you say then, and you'll get essentially a top canopy profile from a plane flying overhead. But if the light can actually, if the canopy, if the forestry is not too dense, so some of the LiDAR light can go down and be reflected from the ground. So when you're looking at the reflection, you look at the last reflection you've got. What you have is what then is called electronic tree removal. So you can see through, as long as the light can go somehow just penetrate through some not really dense forestry, you can then look through that forestry and see what's underneath it. See vehicles, whatever, within a forestry region. So it's a very powerful technology for having a look at what is going on in a wooded area. It has to be said that it obviously doesn't work if the canopy is so thick that you simply get no light going down and reflecting off the ground. Otherwise, you've got a very good technique to have a look what's going on beneath the tree, which is quite surprising. This shows you what's called bunkering, essentially when people are siphoning oil. So if you had a plane flying overhead and you saw those cylinders over there, storage wells, you'd have a very good idea. This is the Transatlantic by the Transatlantic pipeline, so it's not just a Nigerian speciality. You'd have a very good idea that bad things are taking place unless that's deliberate. So this whole business of monitoring your oil pipeline, monitoring anything that's going down a pipeline, is massively important for revenue protection, as folks would say. To give you an idea of the quality, because one of the things is, okay, fine, how about at night time, or how about when it's during rain, or when it's foggy? So this high-resolution synthetic aperture radar, imaging radar technology, actually is part of a data set provided by DSTL, MOD, DSTL, Brightspark, running at around about 30 gigs. And you can see the very high, this is Portland down, by the way. So this shows you the high quality, or the quality of the imagery taken from using a synthetic aperture radar, day or night, it really doesn't matter, fog, haze, or whatever. And you can see, you can get an idea of places where these facilities that are put, dangerous facilities, as we know what goes on Portland down, they would be wanting to put some of these things out of the way. And you can see what's going on, all weather conditions from the UAV. Now the point is, with synthetic aperture radar, you'll have the radar looking down to the right of the plane, or to the left, but not directly beneath the plane, because it's a side-looking, like FMCW, frequency modulated continuous wave type approach. So you can see the imagery is very impressive. It's also quite expensive, that particular high resolution. And no surprise, the monitoring of ships and the like, not just the European Maritime Security Agency, having a look at what's going on south of Portugal and Spain, but clearly the English Channel, because synthetic aperture radar can also, either using visual imagery or SAR, can see oil spills. So if a tanker is throwing oil out to sea that it's not allowed to do, that can be detected. And of course you can pick up little boats and the like, for example in the English Channel if you want to do that. So I'm just giving you an idea of the sensors that you might want to put on a plane and what they can do. Because one of the things you can also do is put an inexpensive, and when I'm saying inexpensive, I'm talking about something like £2,500, radar, marine radar, can be put on an unmanned aircraft. So this will be is a frequency modulated continuous wave. You can get an idea up to 36 nautical miles, what's going on in a line beneath the UAV. And you're talking about, you're not talking about an expensive radar. Just put a standard radar that you will, if you look on a ship and you see a Furuno radar, for example, or an IPOL, this is the sort of imagery you get, and you can say, just stick that on a UAV. And no need for a fancy airborne type radar or anything like that. Just use a marine radar, and you'll see 36 nautical miles is plenty good enough with most applications. Now, one of the things also to bear in mind, so I'm trying to give you an idea of the sensors and the ways in which, what you need to put on your plane if you're thinking of running multiple UAVs. And if we have, for example, the UAV, now we're out at 20 nautical miles or 100, it's like, okay, well and good. And what happens if you want to get the information back, which is what you want to do in a timely manner. Because what happens if you're looking at, and I'll take a military context, but you can imagine with a little ship or a little boat moving along, it's no good saying, well, that boat used to be there 5 hours ago, and heaven knows where it is now. You want timely information. If you're looking in the Ukraine, artillery pieces are moved every 8 minutes. So if you're not acting or doing something about what you've seen within 8 minutes in Ukraine, forget it. Whatever you thought was there isn't there anymore. It's somewhere else. So what do? We start to think of using satellite communications on the UAV. Now, there's a huge change come about, and I'll come into the next slide, whereas previously you had to either use a very, very expensive Viasat. I'm talking about £500,000 satellite edition. I don't mean to give Viasat a hard time, but that's the way it used to be. Small little thing, weighs a ton, and costs the Earth. And then along comes the sister that we can use, let me see now, Inmarsat, which is a geostationary satellite, so that satellite sticking as the Earth rotates, that satellite's in the same location. And you can then relay via Inmarsat. They go through a ground station, so you get your information through a double hop. This is actually in Belgium, and you get your information from the distant satellite. But it's a low bandwidth. So this just shows the top image, shows you the satellite communication system there, the little disk up there. Actually, no, I'll just point to it. Ah, excellent. Thank you very much. But you see, maximum data upload, 400 kilobits per second. Now, if you're looking at video, that's not great. It's not going to happen. You say you're looking at one photograph, and then one, and then several seconds later, another photograph. Better than nothing, but not great. And that's an example near our where we do some flight testing of the quality of the, and you can see how many kilobytes, and it's taken some time to go there, and there you see on the right-hand side. So that is it gives you an idea of the frame, the type of picture that you will get. So clearly on the plane, there needs to be sufficient intelligence that it can decide this is worth sending back to you. So somehow, and if you're into image recognition, there's a thing called YOLO, you only look once, YOLO version 7. It can classify what it sees. Then you say, right, just send me, if you see a vehicle of some particular interest, send me that cutout from the photograph and don't send me anything else. So it doesn't have that interpretation taking place. A, using a lot of bandwidth, B, using a lot of people. You just send me something. But the problem is that it may miss something. So if you see something unusual, it won't send you that information. It'll just send you something you've asked to find. Oops, I need to go back one. No. Right. Enter Elon Musk from SpaceX. His Starlink mobility. So what Elon Musk has done is he's now using low Earth orbit satellites rather than geostationary satellites that are much, much closer to Earth. But these things, like the GPS, have to circle the Earth. And he's got, I think, thousands of satellites up there right at this moment. So you look at the milliseconds round trip. The Starlink one can really do, it gives you much, in fact we use this right now because where we have some of our development work is in a farm area near Bulldog. And we actually use the Starlink satellite. And you can do a video teleconference. The latency is so low, you can do a video teleconference and it's absolutely, you can't tell the difference between broadband from BT or whoever and Starlink. It's really impressive and very good. And we just use that as our link rather than trying to get BT, Vodafone to install a link. So we're looking at around 25 milliseconds because it's low Earth orbit versus 600 plus milliseconds. And it gets better. What they're bringing out, well, maybe it is, and it is at a cost. But you can actually put that terminal on the UAV now, Starlink Roam, and you're looking at now 220 megabit per second download. To be sure, let me say, first, you're looking at £250 a month for the one-time setup, 2,400. But you're getting a very, very impressive communication system that used to be the domain of the Viasats of this world, except the latency is much lower, because Viasat's also using their satellites further out. And the price is, now you're looking, not comparing 2,400 with the Inmarsat price, but you're comparing that with the Viasat to £500,000. Suddenly, the show is on. We've got now radar systems that are inexpensive. We've got satellite communications which can handle video, no problem at all, on the plane. And these can go, but it does come down to, you've got a particular size aircraft that you need to have in order to fit that dish, because you can see the size of that dish. That's not going to go on a small little UAV. But it can be on like an airborne warning and control satellite plane, a plane that's circling an area of interest or on the periphery of an area of interest. And it's got all the other planes nearby that's got a mesh network, for example, that's communicating with, and then it's sending back to base the information from that airborne warning and control UAV. So, looking, and it's no surprise that as you add number of aircraft, so hopping now back to the financial side of things, as you add aircraft, UAVs, to the survey, and you have a look at the cost, how the cost comes down. Clearly there comes a point where the incremental gain is not that great, as you say, go above 4. But there is a very decent gain for just going from 1 to 2. You almost halved your costs. And then you get an improvement, but it's more gradual as you start adding more planes to that. But that could be important. We did for the European Space Agency, we also had a look at the use of multiple sensors to gather the information, use of multiple UAVs, flying day and night. Now this is where you can say, well, hang on a minute, folks do like to sleep. But you say, well, guess what? Folks in Australia, because we've got satellite communications, and Starlink is all throughout the world, handle the nighttime stuff, for them daytime, of course. And folks in California can handle some other things. So around the world, you can have a continuous 24/7 coverage without people having to stay awake at night or anything like that. So you're not paying necessarily nighttime, overtime, or anything like that. Prices to get this type of activity, given satellite communication, and given it's the Starlink, the business, we could communicate with folks in America for the same price as it costs us to communicate within the UK, because it's just sent by optical communication between the satellites, and it goes downloaded. So looking at formations, because there are two key differences here in terms of when you're using multiple UAVs. And one is a formation of UAVs, and another one is then a swarm. And sometimes people might say, or you might hear, this formation is a load of garbage. That's the sort of naughty stuff you do when you're getting into this field. But actually there's an application, a very useful application for formations, and separately a very useful application for swarms of UAVs. So you might look there and think, holy smoke, look at that. And the beauty then is, if one of these birds, let's just say these birds were on a mission and they were filming something on the ground, and one of the birds was feeling poorly and then fell out from that formation, from that swarm, no, it is redundant. It is inefficient, to be sure, because you have multiple members of a swarm covering each other. So the inefficiency gives it redundancy. And if you can then say that you have inexpensive UAVs, so that's the key thing in multiple UAVs, they need to be inexpensive and they need to be reliable, because if they're unreliable and you add more, and then they start falling out of the sky because they're lacking in reliability, again, you've got a problem. So you need to have a difficult, and it's challenging, I think, from an engineering point of view, is that you need to cut the cost and increase the reliability of the UAVs. So I just mentioned that actually the Elon Musk and the Starlink folk, SpaceX people actually turned down the brightness because you started to see that the satellites, low Earth orbit satellites, were starting to annoy the astronomy people because they would be taking these long exposure photographs of stars and just get all these streaky lines from the SpaceX satellites coming over. So what I have here is missions in which a formation would be then more suitable. And I think in a sense this is self-evident that if you're doing mapping, monitoring railroads, for example, radio relay, long-range cargo lifting, radio direction finding, and multiple synthetic aperture, the sensible thing to do would be to use a formation of UAVs. So basically, UAV technology, if you're getting into this field, and I think it's an excellent field that we should all be getting in. You just look at Ukraine, you can see how effective it is. You need to have UAVs that can be switched between operating in a formation, and this is done with the autopilot and the electronics, so the physical plane doesn't change. It's the control of the plane that changes, or change it to be able to handle a swarm, in which you have multiple different activities that need to be done, and you need redundancy. Short range, so where people can change, and somebody say, no, I want this, somebody should go somewhere there, and so the ground control station is rerouting a plane, depending on the situation, for example, and rapid search. So in other words, if we're finding something interesting in a particular location, we need a swarm. And the reason is this, that something interesting that we found could actually be a decoy. So let's just imagine the bank job is taking place here, and we're kind of like going to do the bank. So what we do is we set up a decoy, and we sort of burn the petrol station down nearby. This has the attention of the folks who should be elsewhere. They went down to do the bank. So what you have to do, when you find something, you don't stop and say, right, something bad is happening there. You carry on, but another plane needs to come in to actually have a look at what that was in case it is for real. So for a complex search situation, where you have things that could be decoys and things like that, then you need redundancy, and you need to then have close in. Planes can be rerouted to look at areas of interest. So on the communication side, this is essentially from a commercial radio that we use on the planes. We have the situation, we have point-to-point. So in other words, when we have the AWACS type UAV near the area of interest, so let's just say we're sitting safely at the ground control station. It's 200 kilometers away from the area of interest. Now we have to then have the point-to-point link. And you do get 200 kilometer links. This is not sort of fiction, it's the real thing. But on the plane itself, it has two radios. One is a point-to-point radio link, and the other one is a mesh network, point-to-multipoint. So here can be all the UAVs, for example, that are doing business down, mapping the area or going close in, picking up radio signals and the like. So a point-to-point radio, and we have point-to-multipoint on the AWACS type UAV. Whereas these planes can't do point-to-point, they'll do point-to-multipoint communication with that, and then they'll go back home. So again, there's different radio systems in different planes. So the other point is also that, as I mentioned, you can have different planes in the mission. You can have, for example, incoming, what they call one-way mission planes. You could have planes fitted with different sensors that are in the formation. And so if we're monitoring this area, we might need to retask some planes to go and have a look at if we know there's a lot of activity somewhere, that, for example, a lot of people being detected milling around somewhere here. We have to redirect some of the planes. And then we have the swarm leader, a different type of plane, which is the airborne warning and control type plane.
What altitude are these?
So the airborne warning and control plane is about 10,000 feet. And usually what they would like, the preference would be if it can go up to 30,000 feet. So this then raises the interesting point that are you using a fuel-injected engine, which you typically would need for the 30,000 feet, as opposed to an ordinary carburetor type engine. But this would be the radio control, the radio relay planes, 30,000 feet. These other planes can be typically from as low as 100 feet, which is tricky. And they have then LiDAR, down-looking LiDAR to maintain altitude and barometric pressure, so everyone's normalized to the ground control station, but that may be a different pressure to where the area of operation is, and also you've got altitude differences. But planes that are close to the base would be below 10,000 feet. Partly to pick up radio signals, radio direction signals, so you don't want to be too high. They decide, okay, how high do you have to be? What's your area that one plane is looking for radio direction signals from? And certainly, the closer you are, the more you can pick up covert directional communications if you're down close.
You have to share with manned aircraft, same
Yes,
airspace.
yeah,
So what
absolutely.
about electronic conspicuity?
Yes. So, well, the thing is, so ADS-B, for example, is something that we have to put on the plane, but you have to register it with the Civil Aviation Authority. But clearly, depending where you're operating, you may want to turn your ADS-B off.
Oh,
Because you just have to look at flight radar and just say, okay, hello, there's there. So you turn the
I
ADS-B.
personally don't think ADS-B is the answer though, because it's the bandwidth is too.
For electronic conspicuity.
Yeah, it's insufficient. For a UAV to operate safely, it needs to be able to see and avoid itself.
Now, interesting. Yes, exactly. Because, in fact, on the train up, I'm doing my conclusion to our project that we have with the MOD on collision detect and avoid.
Mm-hmm.
So you're absolutely right. And the question is, what sort of sensor do you... Well, several things comes to UAV collision detect and avoid. And one of the reasons we need it, actually, is because we operate from a civilian airfield. We operate from it's grandly called the Newnham International Microlight Flight Centre or something like that. It's just a strip in by a farmer's field. And the thing is, microlight folk use it, and they don't give a damn about any conspicuity of any description. And they don't even listen to the airborne radio. So we have to make sure that our planes, which are flying at the same time sometimes as their planes, are not colliding with the microlight folk. And so we essentially have investigated the use of optical imaging. But the thing is, if someone says, okay, fine, but I've got a problem with how you're operating at night. Although the CAA do not allow you to operate at night, but we have to make sure our planes do, so thermal imaging camera comes in. But what you need then is detection of the plane and ranging of the plane. So we're essentially using scanning LiDAR for detection ranging, but then backing it up with radar, FMCW radar, because that's the essential frequency modulated continuous wave. This is a standard way to get range. And if you're into, it's actually, it's kind of interesting to see these exhibits up, because a lot of technology actually comes from 1945. It may sound exotic, but actually a lot of good stuff was done.
Squawk code.
So, so if you look at monopulse phase comparator, circuit, we use that as well electronically. It'll give you error to the detection, vertical and horizontal, using patch antenna. Things. We use a combination of electromagnetic at 5.6 gig and the LiDAR.
Have you come across pilot aware?
Sorry?
Have you come across pilot aware?
No.
Well, that's what a lot of GA are using for. It can detect FLARM, Mode S using MLAT. So it's got all the ranging, all the height. It'll give warnings to all the aircraft that you can see.
You know the problem we have. I tell you what the problem we have.
Yeah.
So I hear what you say. What we have is the guys with the microlight. They've got like nothing.
They have.
The microlight.
Yours may not be, but I can assure you a great number have.
Okay. No, fair dues. Yeah. So we have, at the moment, one of the projects we have just done is how can the UAV detect something. So in other words, assume the pilot is either turned it off or not got it or whatever. We need to make sure the UAV is going to avoid the collision, which it does do.
Yeah.
So using that technology. And now, actually, interestingly, DSL, we have very good discussions with them. They say, well, maybe we want to turn it around. Say, collision intercept, so reverse it to actually, we want you to collide with something.
Yeah.
But either way, you have to figure out where is the plane coming, what the trajectory is, what maneuver do you take, and then the rules of the air, depending on trajectories and stuff like that. So on the 22nd, next week, Thursday, we have a very big meeting to discuss end of project on collision detect and avoid for UAVs. So
I'm involved with the CAA. We're doing a study on that, or a workshop anyway, on the same subject.
Right, we're filling out the OSCs for flying big planes, and like RF, Spade Adam, and Salisbury Plane. So Yeah, no, so very good point, thanks. Okie dokie. So the whole business of leaving and joining, because you can have then a situation where you may wish to have a long-term monitoring. So clearly planes will be arriving, planes will be leaving the swarm, and how do you manage that, and how do you avoid a collision of the incoming plane and the plane that's returning to base, for example. And yeah, when I say safely auto-route, this comes down to having collision detection for both own UAVs, other UAVs, and manned aircraft, absolutely. And so that, but I'll talk to you because I'll make a note of that.
Yeah, I'll talk to you after.
Because I have heard of that, but you know, sometimes you hear things, good things, and
Yeah.
forget that. So it's a good, very good point. So although I say you should support, I haven't updated this since this particular slide, since the former one, but collision detect and avoid thermal imaging, so I talked about that. So now we have done that, so tick that off. Yeah, the whole business of retasking, which is quite tricky from a point of view of Civil Aviation Authority, talking about that, where they would like to know where you're going to go. And on exercises, on trials, this is going to be changed all the time. So we have to build in a capability for them to be dynamically retasked, which does get a bit tricky. So, yes. And actually, I don't think, maybe you noticed Jerry Corbett.
I don't remember the name.
Okay, right, because this is us at CAA discussing multiple UAVs. Jerry Corbett is from CAA.
Right.
They're both, I think, the one on the top right, top of the corner there from MOD, the SDL, Adrian Ball, you maybe recognise. There's the CAA people then next to him. And yours truly, I think, sitting there, and one of the characters working with us. And what I say here is, it is massively important, the whole regulatory side of things. In fact, so important, I'm not going to do it an injustice by a cursory coverage of that area. But suffice to say, we've actually got one person fully occupied on sorting out the regulatory. Because what's happened is, just a little detour, there used to be CAP 722, used to be the regulatory framework with which one operated in the UK. And that has now been superseded by CAP 722A, which is a complete rewrite, a complete redo of the operational safety cases. And for any place you're going to fly or hope to fly, you have to fill that in. And with good reason, because if you're looking at for example, in our case, a 70-kilogram plane, 10,000 feet above the air, flying out at what they call beyond visual line of sight, not beyond radio line of sight, but beyond visual line of sight, 12 kilometers away. If this landed on someone, it'll be some serious problem. And so it is necessary, and you do have to go through a lot of, which is why we had to have one person fully on the case. So I say, it is massively important. I won't be covering that. Maybe that'll be a topic for you to give a presentation on at a future time. Right, how to test. So what we do, many people do this, we do the ground testing, simulation of the plane. Then actually what we do is this is a tractor, so you often see this kid's mobile vehicle. We say, okay, we actually put an autopilot in a ground vehicle. So we get several of these things, 10 for example, to check the radio communications, to check the flight, so it's almost like flight in 2 dimensions. Fly these things and just make sure, not fly these things, run these things along the ground, make sure the communications are kept, we get the radio links, everything's working on the ground. You know, obviously if anything bad happens, we just stop it, and so you just got this, everything's on the ground. And essentially, you first make sure the simulation works properly, then you make sure that works properly, then you get to multi-rotors, because these things can be parked in the sky, before you move on to things that can't be readily parked in the sky. So that's the sequence that we go through. And it is painful sometimes, it does take time, but it is necessary, because we have found all along that there have been things that we had to correct prior to moving to the next stage. And what we use is do a flight simulator model, an accurate flight simulator model. For example, this is an old plane that we're doing tests. Just make sure that the aerodynamics were fine, that if we wanted to turn, especially, for example, if we're looking for a maneuver, collision detect and avoid maneuver, do you try and climb over the plane? Ideally, you turn left or right. And can you do that? And what are the sensor ranges? So what are the sensor requirements in order to avoid something that might be moving quite quickly in your direction? what maneuver do you do? So we do a lot of simulation work on that with realistic aircraft simulations. And notice the operator ID. You always have to put your operator ID on your plane. So if it is lost or crashes or whatever, then clearly they can, you see I need to be notified and you've got your identification. And so we have that on all our planes, and that's a small foam wing plane. So, but even on that, you put your operator ID on. And then the UAV pilot training moves on to the standard type of plane we use, which is the VTOL capable UAV. So what does that electric plane has is 4 VTOL, and you can see the size of 3.5 meter wingspan, but it also has an electric pusher motor. So the plane will take off vertically, and this seems to be an increasing trend that you don't want. You just look outside and see this lovely airfield, but if you're in one, it costs money. 2, if you're going to degrade the capability, then I think I'll be putting something over Cosford. It's just as well we're in a bomb bunker, because I'll be landing stuff outside and then it's unusable. You can just see this thing can be used anywhere. You just take it to any field, plane takes off vertically, transitions to forward flight, flies and does whatever you want it to do, comes back, lands wherever you want, comes down, does a vertical landing. Very convenient. You can operate it pretty much anywhere. Using carbon fiber, and one of the interesting things about carbon fiber is I think people often think that it absorbs microwave radiation. Answer is it doesn't. It reflects microwave radiation. Very big difference, because if you're looking at radar cross-section, i.e. how much radar signals would be reflected back at your plane, if you build it out of carbon fiber, you've made a nice radar reflector. So, glass fiber will allow the microwave signals to go straight through it. Boom. All the way. And, but it is heavier and it is less strong in terms of weight. So you have to decide how it is you're going to do. But the VTOL capability is one that we're using, we'll be using extensively, except for the very big plane that does the rotates, AWACS type thing, that's a runway plane, because that can be away from where bad things are happening, if you like. But otherwise we use the VTOL capable planes in all other applications, and as do many of the people that we work with use VTOL capable planes. So that is the way. If you see something that isn't VTOL capable, you can almost be thinking that's yesterday's technology. Just to move on with this progression of how you then handle a swarm. So we first started off with 5 UAVs. You don't really want to start with anything smaller, because that's not exercising anything. You started with 5, and you'll be surprised at the problems that you come across. For example, radio problems. And without naming a large company, they did have experience of a problem in going from 3 UAVs to 4 in terms of the radio latency and the operation of the radio. And everyone would think, oh, how can you have problems? Answer, we can, believe me. So going to 5 is actually a very sensible approach in terms of on your trajectory to doing swarms of UAVs. And if you're doing a formation, you can clearly see here that this is crazy stuff. As you're trying to turn a circle, and if you're having 5 planes flying side by side, you clearly got to do something about the plane on the inside relative to the plane on the outside. Otherwise, obviously silly things are happening. And that's where we can test it using, we just test this business using cars, these little cars on the ground, or with autopilots on them. And then transfer that technology to the bigger planes. So there you see, this was for MOD. Running the 5 planes now that we've got the control of the formation in hand, we're using the Pixel autopilot, which you can go out and buy for about £350, so it's nothing fancy. And using foam wing type planes, and you can maintain separation and control the planes flying as you see there. Then it's like, okay, now let's move the show on and get 20 planes in the air. So there we look at the simulation of 20 planes. We've sorted out the business that if you're doing a turn, and this is actually simulation. So you see it's not idealistic. You can see that some planes are not actually following the previous plane's flight path. But you see, it does look like we've got control of these planes. And where the next slide comes up. Oh,
Yeah.
so, several years ago, about almost just 5.5 years ago, 20 UAVs, first time flown in the UK. And so there you see them all up in the air. This is again funded by the MOD, who were demonstrating a figure of 8 formation flying. And then had quite an interesting effect because there were a whole lot of sheep in one of the fields, and it had the effect of rounding up the sheep. So there we are, because they were clearly not happy with what was heading their way. And the mesh network worked fine because the mesh network is communicating with all the planes. They're all keeping their distance as they're moving along. You know, obviously we had CAA permission to do that. So there's a lot of maths that went into the repulsion, attractive forces and the like to maintain that. But that's formation flying. So 20 planes can be done, radio link can be maintained, they can fly sensibly. And that was again using VTOL capable planes. So rather than trying to have all 20, you can imagine if you're trying to have a runway, you've got all these planes, you want them to fly together, it's a nonsense. So just stick them all on the ground, they all just take off, they're all on their way, they come back, they all just land where you want them to land. So it's so much more convenient, this sort of thing. And it, you know, come on now, you wouldn't want to use a runway for that. Right, the key thing also, in terms of if you think, okay, let's do formation flying, is then you have distributed intelligence. So one of the aims is to reduce what's called the cognitive loading of the ground control station operator. So whoever's managing this, especially the payload operator, you don't have almost a payload operator per plane, because otherwise it's like, hang on a minute, we're not saving much money by having a payload operator. Get the planes to actually do a lot of the configuration. So here you see open source material. You can download this thing, YOLO, this is you only live once. And it can detect, as you see there, draw a box around it. You have to decide what you wanted to look at. And if you want to have got something of interest, you need to train it on that item of interest that you have, give it photographs, different angles, and say, I want you to look for this or look for that. And like you see there, it will then look for a UAV against a cluttered background. And we looked at that from the collision detect and avoid aspect. That could it then classify that thing. You better be really careful, check that one out. On the other hand, down there you can see, you can identify buses and the things automatically from the air. And then you can put a box around them, as I do here, and just send back that to the ground, to the payload operator, and say, look, there's a bus at this location. And so essentially we reduce the poor payload operator, because you know, you get a whole lot of people in a room, and before you know it, they'll all be talking to each other about what they did the weekend, as opposed to looking at video on the ground. So it's a very powerful technology, readily available. It comes for free, you can download it, and it'll run on a reasonable computer. So looking at one example would be looking at monitoring. If someone says, okay, let's look at monitoring that particular area, this is your job. And I can either have one plane flying raster scan. This won't do it because it'll take so long for the plane to come back. By the time it's come back, you know, you won't get a dynamic picture. It won't be up to date, and it's just a non-starter. So, okay. What we do then is we can break down the area of interest into grids. We can decide where is the grid, where do we think something bad might happen? And for example, we might think that actually here we've got a lot of greenery. There's a no-fly area, so don't even look there. Here we still think not much might happen there, it's just like football fields, stuff like that. The road, yes, certainly. So it will take human intervention. But this opens up a very interesting area of, dare I say it, artificial intelligence, which is, and I think one has to be wary of this AI, because it's sort of like magic fairy dust that people often sprinkle on an otherwise poor proposal to say, yeah, it's powered by AI, and it's just garbage. It's either predictive. But I think what's happened with AI is it had promise, then it had a load of hype, people raising money with venture capitalists and the like. But I think now, in the meanwhile, a lot of good work has taken place in the background. So I think now it has actually become really powerful. So in terms of then figuring out and learning what's going on, I think now is the time when that is starting to be applicable, to have a machine start deciding how would you break this down, partition this, given that you've got various UAVs with various capabilities in your swarm that'll come and go. So you've got a complex mission, you've got different UAVs located in different places with different ranges, different dwell times, different sensor capabilities, and you want to monitor this. It's like, oh, this is getting complicated. And so in terms of going forward, I'd say this is a very rich area of potential technical development and technical progress in this area. The flying of the UAV, I think that is pretty much, that's in reasonably good shape, I would say. Regulations, certainly there's room for working on that. But in terms of the planning of the mission and using, for example, reinforcement learning. In fact, I was told it's not in the original from me, or the MOD guy said to me, are you using reinforcement learning? Which is, prior to that, I'd been thinking, this AI, we're going to avoid it like the plague. There's so much fairy dust, it's garbage. Actually, I'm coming now to the conclusion, actually it's not now that it is useful. It is the thing to go for. And it gets a bit more tricky, because let's just say, this is just a simple example that I've just drawn up, that you have decided that you're going to scan something like this. This is just a very simple example that I have. You've got to remember that if you fly over, you give a cost function to flying over a particular area. If you photograph it, you say or a reward, if you like, you get a reward of a certain amount. But if you immediately go over the same area again, you don't get a great reward, because very little will happen. But slowly over time, the value of you flying over an area that you have gone over increases with time, because now something could happen. So you have a time-dependent reward for a particular area. So you could say, okay, you get good reward if you're going over here. You don't get much if you fly over here. We're not thinking much happens there. So you can go fairly pedestrian pace over there. But here, you know, you're going to get really good reward. So if you like, you have to either have a very capable plane, several planes, or cut down the things. So you cut down the latency to try and, so the sizing of that mesh is then dependent upon the reward, and that needs to be done automatically, because somebody could say, look, just look over this whole area, will you? And you then need to factor all that in. So it's becoming quite the planning now, the automatic planning for a monitoring of an area with multiple UAVs is very challenging. It's very rewarding if you can solve it, and it certainly is current research. And also, the thing to do is bear in mind that there may be no-fly areas. So you may say, this is a no-fly area, do not fly there at all. You get a massive punishment, you get a very negative reward if you go over there. So you may have to, for whatever reason, but you'll be penalised big time. So that route planning is something that we are now looking to work with the universities, because I think in this AI business, if you haven't got a background in AI, you haven't done that, they are the people that you need to work with, and that's who we are looking now to work with universities to essentially apply reinforcement learning to this issue. The question is then, if it becomes dynamic, and this is where CAA, we need to also interact with CAA, it's now if we have a dynamic situation. So originally we put an application on flying here, and now guess what? On the day, due to events, we're flying somewhere else. Yeah, we need to have a discussion. But I think things are moving on CAA. I think they are cognizant of developments, and it is a very fast-moving area. So, example number one from the military application that we have is then the ground control station and the good old Starlink terminal. So we can then pick up information from the UAV, go to essentially where we have the pilot command. And here, by the way, we're not operating in isolation. So what I've not drawn here are the companies that we are working with. So we are working with, for example, Kinetic. We are working with other big defense companies. I'm working with the MOD, but I'm not naming them on the slide because it's people we are working with. So this is not a situation in isolation. It is communicating with other players in the field who are talking to F-35s and all this kind of thing. But you see, if the UAV up there, the airborne one, control has a Starlink link, you can see that we have a direct connection to the plane, and we can get video from the plane. And that plane is there, and that's the one that's operating at 30,000 feet, for example, is a typical altitude for the AWACS type plane, as we call it. Then the lower planes are coming in, looking at what's going on in the ground, for example, at the ground, flying in that particular area, lower down. Now, and then it's smart because this is one way again the interaction with the CAA comes to the fore, is what we have as a capability is to carry, for the planes that carry another plane, so you have an air-launched swing wing plane that can be air-launched from that thing, or an air-launched gas turbine-powered delta wing plane. So if we need to act quickly, clearly if we are now 200 kilometers away and things are going to move, and say we have a target of opportunity, like a high-value target like a jet, that we decide in, and it's well, going to do something about it. We can't now wait for a plane to come in from 200k away to deal with it. So what happens is then we release a smaller plane, airborne release of a smaller UAV. And so it's like the American Switchblade, but they launch it from the ground, we launch it from the air. We haven't tested any in the UK, you'll be pleased to know, so far. So that is the next one. And again, we need the communications. And suddenly the swarm has actually increased in size without bringing any planes in from the outside. So we can bring planes in from the outside, but we can also increase the size of the swarm by air launching UAVs from the planes that are in the area of interest. Right, so I've covered some of the topics, and obviously I thank you for your interest and for your being here, and hopefully given you some idea of the difference and importance, relative importance of a formation of UAVs and a swarm. Now, I think some of these are obvious. Simulation is the way to go forward. Structured test early and test often is the approach that we take, rather than try and plan everything out and then hope on the day that good things will happen. It's essentially do this incremental approach to start simple, just try and get your little swarm to work on vehicles on the ground, because if you can't get that, then you've got work to do. And I would obviously like to thank very much the folks that have supported the work that we do in the past and continue to support it. We're very thankful, MOD, Innovate UK, European Space Agency, Kinetic. And thank you very much, Darren, for the invitation to give the presentation, and to Tony for appreciated help. And certainly any questions, I'm happy to answer them as you are now, or if you would like to discuss them, come up and discuss them, that would be great. So thank you very much.
So, any questions?
Could you mention something about countermeasures? Obviously, uplinks and downlinks can be attacked.
Exactly. So, what bad things could happen, right? One is that GPS, the most common one is GPS is jammed. And you have to count on it being jammed. So the question is, so now what are you going to do? And I'll just give you the countermeasure to that is, or sort of countermeasure if you like, is one is to try to use, and the first time I heard this phrase, CRPA, and the expression on your face was the one on my face as well, like what the devil is CRPA? This was in a military environment where acronyms just flow freely. Controlled Radiation Pattern Antenna. And what that is then is like 4 GPS antennas or more, and essentially nulling out, because the problem is that jamming can come from high up, it doesn't necessarily come from the ground. So if it comes from high up, you can say, well, shield your GPS antenna. Well, guess what? If the jammer is upstairs, also at 30,000 feet, then you've got a problem. So you can spend £7,000, you get yourself a CRPA, and it can jam 3, it can null out 3 jammers on that thing. Now when I say null out, it essentially introduces about 40 dB of attenuation of the jamming signal. So if the jamming signal is super strong, that won't be 40 dB, still it will mean that you are still jammed. So that's the first one you could try. But the problem is that you have a cost function, £7,200. So it's like, not happy about this incremental price increase. The other thing is then to get yourself a very good inertial measurement system. And what you have to then get is a 6 degree of freedom. So you've got magnetometers and accelerometers. They're reasonably well done with silicon microelectronic MEMS. I'll just leave it at MEMS, I should know. You can get that, and then you get a separate magnetometer. So you get a 9 degree of freedom inertial measurement unit. The magnetometer won't drift. Clearly, it's just measuring the Earth's magnetic field. But accelerometer is the weak link,
Yes.
because you can get a very good gyro. You can't get a good quality low drift accelerometer. So that is a big pain. So if you're looking at a situation where the acceleration is subtle, like the wind, so you say, well, just look at which way the plane's flying. Well, it could be crabbing, so it's actually flying in that direction, but not pointing in the direction of flight. So you can't just say that's where it's flying, because it isn't necessarily. But you have a force from the wind, and if you don't pick that up, in amongst all the vibration in the plane, you've got a problem. So trying to get a drift, it's really hard to get a low drift MEMS unit, but sometimes you have to do that. It's the best you can do, and that's that, and try and sort of come home on your, but then you haven't done your mission. The other thing is you can try optical navigation, so looking down the ground, look at optic flow, for example, or if you see a pattern, so you use the YOLO 5 to look down and you fly over known features, so if you go over a church or whatever, bam, you look for that, and you take out the drift. So the GPS jamming is the worst. Communications is bad, but you can get around it. Using very directional communications is one approach. They don't use omnidirectional things. I won't cover some of the other ones, but there are other ways to do that. So I'll have to pass on that one. There are quite a few bad things that could happen. One is what they call directed energy weapons. So if the folks, and you know, a lot of big US, UK, Russia have these things. Israel. So it is high power lasers. You're looking at 50 kilowatt laser to do damage to the plane, or you're looking at high power, like it's almost like shining a radar at the plane to try and fry the electronics or to jam the electrical systems on the plane. So, but that's highly classified. We had to do a project on resilience of that, and as you can imagine, it is highly classified. So you've got DW resilience. Then there's another one, which you could say, that's pathetic, but that's the way it is the inability of inexpensive UAVs, and they're sometimes expensive ones, to fly in windy conditions. So often I've been at military trials where many companies have been participated, and none of us have been able to fly in the wind. So the good news about the very windy conditions we've seen recently is that it's a fantastic place to try a plane if you have any view that you can fly in the wind, because most planes can't. The number of times trials have been, the trial duration has been cut in half due to windy conditions. It's just staggering. And the strange thing is, it's almost like no one is tackling it, or very little effort is going in to getting a plane that will fly in windy conditions. And you know, one can say, guys, come on, how difficult is this? What is the problem here? And the answer is that folks will be working on sensors. There's so many interesting things to work on that the airframe often is not worked on. So I'm just hoping folks in the audience might feel like there's a challenge. Get a plane that will fly in a 50-mile-an-hour wind, and don't come talk to us until it does. Is the name of the game. And you know, it can be done. It's just just put a finger up and get the show on the road. So windy conditions, strangely enough, windy conditions. So it's embarrassing, but it's the fact.
That's good.
Okay, thank you.
Sorry, thanks.
Oh, it was related to that. It was the security of the Starlink. They seem to rely a lot on Starlink, so it was a little bit related to lasers. How secure is that potentially?
Well, I think it's not, and I think you have to assume ab initio it's not. And I think at the end of the day, very little relatively inexpensive things are inexpensive, are resilient to being intercepted. So my feeling is, one, you have to make sure your UAV can operate without any radio link, can come back if it detects. First thing, can you detect that bad things are happening? And if it's payload, so the idea is then you have to be careful. You have to decide whether that link is going to be just for payload, not for command and control. If it's command and control, then I think you're onto a sticky wicket. My feeling is that. But if it's sending back information, then okay, so if someone else picks up that you're photographing this, it's not great, but it's not the end of the world. The key thing, so there are actually two channels that I haven't covered. One is the payload channel, which is usually wide bandwidth, and then a narrow bandwidth command and control channel, which is quite separate, usually different frequencies, and that is then more secure. And there are companies in the UK who are working on secure radios for long range, for command, but only for command and control. So you're looking at 10 kilobit per second type things, and they'll be just sending go here, go there, or come home, or something like that. So you do separate out command and control and payload. Yeah.
Thank you.
Is there a problem with Elon Musk and military use of Starlink?
I'm not a big guru on that, but I know he was turning off the Starlink service in Ukraine. Well, I think he might have turned it on. I'm not a guru on that, but I think, you know, being a business person...
I don't think it was ever turned on.
Sorry?
I don't think it was ever turned on, that was the problem.
Yeah. You know, it's one of those things that if you use it, you use it, but if it's not turned on, then you have to reserve that for civilian or security, like oil pipeline, and just say, actually, no can do, in which case you then fall back to the radio link, because we do have 200-kilometer radio link that we do use directional radio to go from the ground. Well, first of all, we have a link from the ground control station to the AWACS plane, and that can be up to 200 kilometers. And then that is another. Then there's another link. So if Elon turns off the system in, say, Ukraine, let's just say were we to be in Ukraine, then we maybe won't be using Starlink. We'd be using our own directional radio.
But there's nothing in the Elon terms and conditions that says you will not use this for military purposes.
You know, I've not read the terms and conditions.
Just tick
Yeah. But you know, I'm sure we will be told if it is the case. So, you know.
Nice to Elon.
Any more questions? Next, stunned silence. Okay. I'll step in at this point and offer my very sincere thanks for tonight's lecture. Over the years, listened to many talks, and what I relish is the ability to learn from what you've been talking about, but also to get a feel for how different parts of the aerospace sector are developing, and the innovation and the ingenuity that's being used, and looking forward to the future in this sector. Particularly, you've really given us a feel for that, and I'll come on to that in a little while, particularly when your last summary, couple of slides that gave almost like a working example of how you use it to map out grids. I found it quite a compelling narrative. And actually, you know, I've got a background in aerospace, but I don't have a background in UAV, and I guess I've got a mixture in the audience here tonight as well. So I guess for some people, there's an awareness of what we talked about, for many of us probably not. So what you've done, and I thank you for that, is you've kind of put quite a nice narrative together. And you've talked us through, reminded us some of the uses from the military, which I guess most of us got an idea about. Some of the examples, the sort of degree of penetration through wood, that wasn't something I'd got a clue about. So you showed the sort of scope of the activity we can do as well. Building on that, you know, some little bits of information that certainly I didn't know about. You know, you've got the idea of 3 people controlling a UAV. I think I knew we were going to pilot, but then how that moves up and the advantage gained by having sort of 5 units. Again, this is really important, really interesting information that I've got a clue about. I guess many of us haven't. And then for me, you talked about, really started to sort of talk to us about the difference between swarms and formations, which for me was terminology I'd heard thrown around, but really helped to articulate it. And then little things I enjoyed about your talk as well is sort of the ground testing, where you've got those sort of robot trucks. Again, thoughts that if you're not in this environment, you maybe not thought about. But what I really enjoyed was you find a couple of slides where you kind of pulled it all together, and you really showed, and then you brought in the thought about AI as well. And until you mentioned it, I'd not made a link about the technology you're working on and the applications of AI. So maybe there's another side to what you've talked to us about tonight. It's actually, do you know what, technology might seem slightly scary, like AI is quite a big thing, isn't it? It's coming into the fore at the moment, like you said. But actually, maybe there are applications, and it's great to see the innovation out there to try and bring these different things together. So look, thank you very much for a fantastic talk. Cheers.